Let's spend a few minutes discussing the differences between stereoselectivity and stereospecificity. And as we read in the book, we know that stereoselectivity will produce two stereoisomers in different amounts, in unequal amounts. And of course, we're dealing with eliminations, and so we're talking about alkenes as our stereoisomers. So basically E versus Z. And we can look at that here by observing that we have a small base. We're going to have two hydrogens next to our bromine. And in this case, we don't really have any difference in terms of the positions of these hydrogens. These hydrogens over here are also going to give us the same product outcome. So we don't really have anything to worry about in terms of the location of the product, the regiochemistry. We know that the alkene is going to form basically right there. But how does that happen? Well, let's look at the two different products that we can form. And let's do Alright, so here's the E, and this is the Z product. And we know that E alkenes are typically more stable than Z. And because our reaction has essentially a choice, we can call the E product the major product. How does that form? Well, it actually requires a Newman projection to look and see. So you don't actually need a Newman projection here, but in order to visualize how the E and the Z products form, we need to look at a Newman projection, and it turns out that the E product will form from loss of HA, and the Z product will form from loss of HB. And I'm going to prove that to you right now using a Newman projection, and I'm going to look down this arrow, this poorly drawn arrow, for my Newman projection. So if I do that, I'm going to get the ethyl, the bromine, and here's where you saw that when I told you that Newman projections will be useful in the future. Now we see why that is. So I have a methyl, and then I have my two hydrogens. HB is on the same side as the bromine, and HA is on the opposite side of the bromine. And so we know that for E2, we want anti-paraplanar relationship between the beta hydrogen and the leaving group. So basically that means we need 180 degrees between them on our Newman projection, and indeed we have that with HA and the bromine right now. These are 180 degrees from each other. And so if I then make an alkene, I'm going to have these groups that I circled in blue on the same side of the alkene. And so let me put HB on my alkene right here, and you'll see that it's right there. And this one is HA. And so I have the methyl and the hydrogen are on the same side of the alkene, and I have HB and the ethyl on the same side of the alkene, and you can see that right here. HB and the ethyl are on the same side of the alkene, and that's what I get from this Newman projection. So let's take this now and rotate it 120 degrees, so 1/3 of a rotation, so that I put HB opposite the bromine. Alright, so now I have HB opposite the bromine, and so I can undergo an E2 reaction from this Newman projection as well, and that would give me the ethyl and the methyl on the same side, and I see that right here. I'm going to use red. I see that in the Z version, the methyl and the ethyl are on the same side, and then, of course, the original hydrogen next to the bromine is right there, and that is next to the HA. And if I were to ask you way back in Chapter 4, which of these Newman projections would be higher in energy, you should tell me that the first one has lower energy because the two large groups are opposite each other. And this one has higher energy. Not the highest energy, because we'd look for an eclipsed version, but this one has higher energy with the two large groups having this gauche interaction. And so it's going to be harder to get to this Newman projection and achieve the loss of HB, and thus it's going to take a shorter time period to get to the E version, because it has a lower energy transition state. So let's just write that down here. And so we do have a choice here, and of course we can look at our and this transition state here is loss of HA, and this transition state here is loss of HB. And so you can see that the loss of HA transition state, which comes from this Newman projection, is lower energy, so it'll be more easily achieved, and thus it'll lead to our E isomer more often. So we get an unequal distribution, but we still can produce E and Z isomers because we have, in our original structure, two hydrogens to choose from on the beta carbon. So that's stereoselective. What about stereospecific? Let's look at that. And so here we have our bromine. It has only one beta hydrogen. We're not even going to label that HA or B. There's only one beta hydrogen. I'm going to put on the other hydrogen that doesn't play a role in the reaction, but it's just there, and we want to be able to keep track of it as we go through our discussion. So let's look at, again, a Newman projection, because remember, we need to put the hydrogen 180 degrees from the leaving group. And if we draw the Newman projection, we get, there's our red hydrogen, and I'm going to use blue for the other hydrogen so we don't get distracted by it. It's just a hydrogen. It's not going to be removed. And so you can see that this Newman projection is already set up for the 180 degree relationship. Sometimes it works out that way. Other times we may have to rotate the Newman projection. So now we can remove the H and the Br. Remember, there's only one choice here, so it doesn't matter what the size of our base. It doesn't matter what everything else is. All we have to do is rotate our Newman projection so that the hydrogen is 180 from the leaving group, and that will give us an alkene that has the blue hydrogen and the ethyl on one side of it, and the CN and the methyl on the other side. And so let's go ahead and draw this, and I'm going to draw the product right here. I'm going to keep the same relationship for now. I'm going to put my alkene right here, and I know that the methyl and the CN should be on the same side of the alkene, so they should be cis to each other, so I'll put the methyl right here, and then my blue hydrogen I'll put right there, and that's on the same side as the ethyl. And so this will be the only stereoisomer formed. And that's where we get stereospecific. Only one stereoisomer is formed. It doesn't matter if it's E or Z. In this case, we have our two large groups across the imaginary line from each other. So this is the E version, but it could very well form the Z version if we had different stereochemistry in our original structure. So here we have just the one hydrogen, and that will result in only one possible product formed. So this is the only product, not the major product. This is the only product in terms of E2 reactions. And so that's the difference between stereoselective and stereospecific. They can both be solved with Newman projections, although up here in stereoselective we don't really need the Newman projections. I just use them to show you how HA and HB can result in the two different E and Z stereoisomers. Whereas down here, only one beta hydrogen, the red one, it has to be 180 from the leaving group, and we did that in our Newman projection. Thus, that helped us decide on the stereochemistry in the product, and that's going to be the only possible product that's formed because there was only one beta hydrogen.